Hello everybody, so we are back for another round of our DMD questions, and on week 5, day 1, we're going to be covering on factors and multiples. So let's look at our table of content. Today, we're going to be learning a little bit of our properties of factors, prime factorization, highest common factor and lowest common multiple, and our factor theorems. And we can use these methods over here to apply to again another question inside our NMOS book. So let's learn some basic properties of factors. So if we see that in this case, A is a factor of B and B is a factor of C, we can actually say that very conclusively, A must be a factor of C. And let me give you an example in this case. If let's say we can say that 2 can divide 4 and 4 can divide 8, we can actually apply that in this case, 2 can divide 8 as well. Let me tell you, this is going to be very helpful for you for one of our questions later on in our inclusion and exclusion. And let's say we look at another method over here. Okay? A is going to be a factor of B and A is also a factor of C. This will also be able to conclude that A would be a factor of B plus C and A can also be a factor of B minus C. Whether we sum the multiples or we subtract away the multiples, we find the difference of the multiples. It also applies over here. Let me just give you a quick, simple example. 2 is able to divide here 8 plus 4, and 2 is also able to divide 8 minus 4. Now, this makes sense. So, in this case, let us understand again about prime factorization. Now, at this stage, many of you should have already understood how to do your basic prime factorization, but let me just run through it very quickly. So, let us think about a more basic number. And I think this number over here will be very helpful for us because this is very, very applicable to this year. So in this case, whenever we do our prime factorization, we try to divide by a number, okay, the smallest prime factor, and we try to do it consecutively all the way to the end. Because in this case, for prime factorization, our outcome is to write our number in a new set of multiples of prime numbers. So let's think about this. We divide this by 2, we're going to get 1, 0, 1, 2. If we do it again, 2, we're going to get 5, 0, 6. If we're going to do it again, 2 will give us 2, 5, 3. And if we go and divide this by, a little bit difficult, I'll help you here. It's going to be dividing by 11. Then we're going to get 23. And once we notice that all numbers here are prime numbers, we can actually conclude that this is going to be the prime factorized form. And how are we going to write it? 2024 equals to 2 cubed, because we use 2 3 times, multiplied by 11, multiplied by 23. Now, using this, we can actually also learn how to use the methods of lowest common multiple and highest common factors as well. So let's give you an example here. Okay, the highest common factor actually talks about between the factors of, let's say, 2 or even more numbers, we are trying to find the highest one. For lowest common multiple, similarly, it's looking through all the multiples of a set of numbers, and we're trying to find the lowest common one. So let me just give you a brief example of 45 and 60. We'll explore both the highest common factor and lowest common multiple. One of the easiest ways over here is actually to go and use your prime factorization first. So if we look at 45 and 60, we can learn to go and apply the prime factorization first, where in this case, 45 is going to give us 3 squared multiplied by 5. But what about 60? In this case over here, we can get 2 squared multiplied by 3 multiplied by 5. So once we have gotten these two sets, we can actually find the highest common factor or lowest common multiple very easily. Highest common factor, find any number, any pairs of number over here that is common between the two, and we want to find the highest common one, which means that we're not looking at the largest possible power. We want to find the power that fits both cases. In this case here, 3 to the power of 1, 5 to the power of 1. 3 to the power of 1, 5 to the power of 1. We get the value of 15 very easily. What about 2 squared? What about the lowest common multiple? We see here, we're going to find anything that is either in both cases or it applies to both as well. And in this case here, lowest common multiple, 2 squared, multiplied by 3 squared, multiplied by 5. We are finding the powers in this case that is the largest one. Again, a common multiple. Okay, it doesn't mean that it has to fit In this case, it has a multiple that has to fit both, but we can actually see the multiples much later on as well. In this case here, we can see the largest multiple, okay, a very big multiple here, 2 squared times 3 squared times 5. Basically looking for the largest possible powers of all of these prime numbers. So after we go and multiply all these numbers over here, we're able to get the value of 180, which makes sense again. Let's think about this. 3 times 60, 4 times 45. It does give us 180. So from this point, we also can actually learn how to apply the previous techniques in prime factorization for your factor theorem. Factor theorem is basically one of the methods you can use to go and calculate the number of factors easily. And in fact, it's a very common method that is used in your NMOS paper. So later on, please remember to also learn how to apply these methods over here in our DMD questions. Let's give an example for the number 2024. So 2024 is basically equivalent to 2 to the power of 3 times 11 times 23, as we explored from early on. And how do we use this to go and determine the number of factors? Some of you may consider listing out all of the factors one by one. However, what if it actually gives you many factors? Are you going to list them out everything one by one? There is actually a quick method over here. And let me start off first by listing for you some of the possible factors of 2024. One, we have, let's say, 253. Let's say we have 1012. We notice that each of these numbers over here is definitely a factor of 2024. We just proved to you in your prime factorization from early on. Now, these numbers over here, believe it or not, it's actually a mixture of your 2, 11, and 23. And how do we get them? Let's say what? 2 to the power of 0, 11 to the power of 0, 23 to the power of 0. Do you remember that we actually explored this previously? Then what about 253 here? So we have 2 to the power of 0, 11 to the power of 1, and 23 to the power of 1. Just 11 times 23 already gives us 253. Then what about 1012? 2 to the power of 2, 11 to the power of 1, and 23 to the power of 1. So basically, just by using a little bit of combinatorics, where we can consider the powers of the numbers, let's say starting from 0, because it actually gives us anything to the power of 0 gives us 1. We can start off with 0 all the way to not exceeding the powers given here. Okay, so in this case over here, we can consider the number of factors to be very easy to determine. Okay, we can range from 0 all the way to 3. So it's basically 4 possible numbers, right? 0, 1, 2, 3. So basically, we can take 3 plus 1. Okay, the powers of 3. Okay, but remember 1, 2, 3, but we must remember to add the 0 behind. Followed by 11 to the power of 1. We can use 1 plus 1. And after that, 23 to the power of 1, we can write 1 plus 1 again. Because remember, again, there is the power of 0 that we must consider. So this gives us 4 times 2 times 2, which gives us 16. You see, I can actually find a very quick method here to go and find the number of factors, and rather than listing out one by one. So last but not least, let's go through one of our NMOS questions. It's a question from very long ago, but we can still apply this method really quickly. The number 144 can be written as a sum of its equal parts. For example, 144 equals to 48 plus 48 plus 48. And the same thing goes for 24, 24, 24, all the way. But at the same time, we cannot use these numbers over here. And let's say we can't even use when it's equal to itself, because there are not equal parts. We have to have more than one number here. But notice that each of these equal parts over here is actually a factor of your 144. So we can actually do this question very quickly. All we need to do is to do your prime factorization for 200 first. So we can actually practice a little bit of prime factorization at the side. 200, when we prime factorize, divide by 2, divide by 2, divide by 2, divide by 5, and we divide by 5. So we can see here, our prime factorized form of 200 is 2 to the power of 3 times 5 squared. And we can really find the number of factors inside this number. It's basically, remember, 3 plus 1 multiplied by 2 plus 1. This will give us 4 times 3, which is 12. And you will think that we can conclude our answer like that already. But remember again, 144 equals to 144 is not considered. One of these factors over here would have been 1 times 144. 144, not included. So we need to remember to subtract 1. The final answer, 12 minus 1 to give us 11. So last but not least, please, as usual, remember to do this. Please remember to complete the 3 questions that are being sent out later on. You can actually use the factor theorem to really help you out later on. Please remember to send your answers inside the group chat for it to be marked and take note of the solutions again on the next day. Thank you, everybody.